Thanks for coming along. Got a couple of people waiting on the YouTube channel. Got 3 or 4, and they're kind of coming and going. So today we're going to be running through. Let's see if I can pause that. We're going to be wading through our energetics topic today. I'm going to do the usual thing. I'm going to be going through a crash course with you guys, covering all the spec points, going through some of those really important bits that are going to be coming up regularly on your exams. And then I'm going to end the webinar on going through the preliminary work that you guys were set at the beginning. Hope you guys have all managed to complete it. I hope you guys have been making the effort to have a look at the follow-up work for the other webinars. But okay, let's crack on with energetics. I'm going to do my usual share screen and drop into my notes. Okay, right. So doing my usual routine, going to run through the learning objectives that I'm hopefully going to achieve. Got Johan saying hi on the chat. Hey, yo. So, yeah, going to be running through. We're going to be defining exothermic and endothermic. And you can see from my little arrow that I'm going to be having a look at the associated graphs that go with this. Hey, Weijie, thanks for coming. Second learning objective, going to look at the understanding of bond enthalpies. It's nice to see my mexo-bendo rules there, which are always really, really useful on helping us remember which way round it goes. Mexo is the making of bonds, is exothermic. I'll clarify this in the notes shortly. And bendo is the breaking of the bonds, being endothermic. Then we're going to be able, I'm going to go apply that understanding into bond enthalpy calculations, where we're using our equation BERP, which is bond enthalpies equals reactants minus products. I will actually expand on that a bit. BERP is a very simplified equation, and I'll expand on that shortly. My fourth learning objective is we're going to have a look at recognizing and knowing internal and external calorimetry practicals. And it is really important, year 11, that we make that and we recognize the distinction between the two practical setups and why one of them is preferred over the other. And we will then look at all the associated problems that go with these practicals. Okay, the last learning objective is be able to use Q equals MC delta T and delta H equals Q over N. So I will expand on those throughout the webinar. Okay, so the next thing, of course, I've done is I've gone to your specification, gone to the igcse edXL specification for levels 9 to 1, and I just cut out the section on energetics. So all the way through the webinar, I'll refer back to this, and hopefully we'll see all the points in this are covered to give a really good, solid overview of energetics as a topic. Okay, so the first thing I want to quickly mention is this title of energetics. And it's one of those words which students at times don't really recognize, or perhaps don't hear enough for them to really recognize it, and for it to be commonly well known and well understood. The word energetics within chemistry as a subject is the study of heat energy. Notice that I'm not just writing heat, I'm not just writing the word energy, I'm putting both together. The study of heat energy change. So that is super, super important. And realizing that we are specifically focusing, on heat energy here. We know when you study physics at Key Stage 3 and Key Stage 4 that we realize that energy can take many forms. It's nice to link in the conservation of energy, the law of conservation of energy, and that energy can either be created or destroyed, and that we transfer it. Well, energetics as a topic within chemistry is the study of how heat is evolved, it is either produced or absorbed, released or absorbed within chemical reactions. And these words, heat energy, is vital. Now, what we wanted to then do as chemists was to give this a singular word, and we did so. We gave this word, this heat energy change, got coined as enthalpy. And that word you'll recognize from all of the exam papers that you've been doing. And that's why it's nice for me to begin with the topic title of energetics, the study of heat energy changes, and then that we coined this term in chemistry as enthalpy. And enthalpy itself has a definition. Now, that definition is not required at GCSE, but it does make an appearance at A level. And enthalpy is the heat energy change under constant pressure. It is the original definition coined by the rather forgotten chemist called Berthelot, who was a French chemist who was one of the founding fathers of energetics. He not only did he coin the term enthalpy, he also coined the terms exothermic and endothermic, which we'll be talking about shortly. So the word enthalpy means heat energy change in a chemical reaction. Now, Berthelot, then, you'll notice my terrible French accent that I'm doing there, not only did he give it the name, but he also gave it a symbol. And that symbol, the symbol for enthalpy change, is delta H. And I should really, you know what, I should really try and make that triangle really a solid triangle. So that there is a triangle, which is actually in the Greek maths people might recognize it, and it is a capital. Oh, nice one. It is a capital. Try again. A capital delta. Now, in chemistry, that symbol, the triangle symbol, the capital delta, means change in. And that does make an appearance in chemistry papers, so it's nice to do it. The capital H, of course, you'd all recognize as heat energy. And that's important. Lots of people just quote it as heat, and that's not allowed. We need to emphasize this idea that you must use the term heat energy. Students often ask me why. The reason being is there is a difference between heat energy and temperature. And heat energy is the total energy change, the total heat energy change in a system, rather than temperature being a measure of vibration. So if I were to have 2 particles vibrating slowly, if I had 10 particles vibrating slowly, they would have the same temperature, but they would have different heat energies, because you have to take into account the number of particles in the system, so the total vibration of a closed system. So we've got our capital delta, meaning change in, and our capital H, meaning heat energy. And all of that is then pulled together in the symbol for enthalpy, the heat energy change under constant pressure. Students then often ask me why the constant pressure, and that's because pressure, if you alter pressure, you will alter heat change. And this does come into chemistry every now and again. If you raise pressure, you will increase temperature. If you decrease pressure, you will decrease pressure. You will decrease temperature. So you don't need that definition for GCSE, but it's nice to kind of talk it through and have a bit of extra detail. So energetics is the study of heat change. Now, for those students who have me in class, they'll recognize the next image, because the way I tend to teach energetics in lesson is I tend to split it into 2 categories. So we have got theoretical calculations, calcs, followed by practical methods. And at that point, I then tend to add in some more words, and I'll change my color for this. So the practical methods are commonly now referred to as calorimetry. Calorimetry is the practical method for measuring heat change. It's nice to have the definition for that. The practical method for measuring measuring heat energy change. Once again, notice that I'm always saying heat energy rather than heat energy change. We then have theoretical calculations. Now, these at GCSE are very straightforward, and these are bond enthalpy calculations. Bond enthalpy calcs. So these ones are done purely on a theoretical basis. We can calculate what the heat energy output would be for a reaction. However, we can then do them practically and compare them. And of course, I would assume that everyone in this room would realize that the theoretical calculations will produce bigger numbers compared to the practical methods. So if we do calcs versus prac, we all know that the enthalpy change measured on the calculation side would always be greater than the enthalpy change on the practical side. Hey Ben, thanks for coming along. What's up? So it's nice to see that we all recognize this, and of course, all of you who've been practicing your past papers now will be seeing on a regular basis, which is they're going to ask you suggest, everyone hates those ones, suggest reasons for discrepancy, suggest reasons for difference in values, and difference in values. And at this point, it's nice just to throw in a few. So answers to that particular question, I'll put it out to the class. I haven't got many people here. Would anyone like to suggest one reason? In fact, I'd like you guys to give me the number one reason for the practical having a smaller value than the theoretical. The answer is heat loss. Heat loss to surroundings. Top answer. And we have to do an awful lot to try and get heat loss to the surroundings. Weiji, well done, outstanding. So heat loss to the surroundings is number one. But of course, we all know in this room that they're going to remove that one. They're going to say, suggest a reason for the difference in values, ignoring heat loss. So whenever you do this, you always learn several reasons. The second one is an incomplete reaction. So maybe the reaction didn't finish. A very good reason. If a reaction is incomplete, you'll produce less heat. The second one is side reactions, alternative reactions occurring, producing less heat. Alternative reactions occur. The next one is impurities. Impurities in reactants. If we weigh out 10 grams of magnesium, in reality, we'll not have 10 grams of magnesium because it's never going to be 100% pure, which means even though I'd be using 10 grams in my calculation, I'm actually going to be only reacting 9.8. So impurities, these are just a few of them, and we're gonna see a whole load more of these appear later on. Okay, so what I'm really doing here is just laying down the foundations of realizing energetics is a topic of studying heat changes in chemistry, and that there are two particular branches of this particular topic, especially within GCSE. Those two branches maintain into A level. You gain more details and extra calculations for the theoretical branch, but they still stand, and the practical methods are expanded on in terms of their detail. But they essentially remain the same when you follow them over. Okay, so at this point, I'm just going to go into the main two words that, of course, we see on a regular basis. So key facts. I just want to do a couple of bullet point facts. Number one, all, and this is important, all reactions, no matter what the reaction is, no matter how small, no matter how similar, all reactions will produce a heat energy change. A heat energy change. All of them will do this. Now, I will then clarify and say, I'll come back to that in one moment. So all of them produce a heat change. Secondly, they are either exothermic, and at this point the definition of this appears. So exo comes from the Greek exon, meaning outside, is where that actually comes from. So this one is a reaction that releases heat energy. Don't ever say them without each other. That releases heat energy to the surroundings. Now, I don't really remember those words. What I have in my head is an image, and the image I have, and of course I'm going to color code this. Why wouldn't you? If you have an exothermic reaction, then it is giving out heat, and the heat is exiting. And of course, the next thing I really want to emphasize here, and I can't stress the usefulness of this, and this will feel hot, and that actually is quite important, and it's quite a grounding thing to have solidified in your mind. Exothermic reactions feel hot. The reason why is because if you have a reaction that is giving out heat energy and you put your hand nearby, that's a terrible hand, you put your hand nearby, if your hand started at 25 degrees Celsius, which is just above room temperature, I mean, it would be more like 32, really. Your body temperature, average core body temperature is 32, but let's call your hand 25. It will absorb that heat and the temp, and it will rise. So your hand will raise in temperature because it's going to be absorbing the heat being released by the reaction. The next one, of course, is, so if they're exothermic, the opposite, of course, is endothermic. Either exothermic or endothermic. Again, the word endo comes from the Greek for internal or inner, endothermic, and of course thermal or therm meaning heat. So this is inner heat, and this is a reaction that absorbs heat energy. Notice I'm never ever not saying those two together. Absorbs heat energy from the surroundings. And at that point, it's nice for me to then again draw the image. I'm going to color code it once again. This time I'm going to switch for blue. And an endothermic reaction is going to be absorbing that heat energy. And it's again super important to have it very clear in your mind that this one will feel cold. Now, people often find that one much harder to accept. Students don't quite understand how a reaction that is absorbing heat would feel cold. And the reason for that, of course, is because the reaction is going to be stealing your heat. So if you put your hand on a chemical reaction that is endo, then your 25 degrees Celsius hand is going to be giving over its heat energy, and it's going to be drained from you. So your hand will decrease in temperature. It's nice at this point also to add that in as well. So if an exo is releasing heat, it feels hot, therefore, it's always nice to do the therefore symbol, temp will increase. It's always nice to just make all those connections and make them clear and solid. And of course, an endothermic reaction will be absorbing heat. It will make you feel cold, and therefore the temperature will decrease. Now, at this point, I'm continuing with my facts and with this train of thought, because at this point we can now give them symbols. Because we already realized that the Berthelot, oh, my terrible French accent once again, Berthelot coined the term enthalpy and exothermic and endothermic, and at the same time he gave them their symbol. So an exothermic reaction is delta H, meaning change in energy, and here's the important bit: the reaction is losing energy. And that's that. I cannot stress how important this is. I'm going to highlight that. Minus delta H means losing heat energy, and that is the symbol for an exothermic reaction. It has a negative enthalpy. And of course, the endothermic one is positive delta H, which is endo, and that is, it is gaining heat energy from the surroundings. So really nice to kind of put and to really focus in on the importance of that. I'm gonna now also say that the one of trouble here, and I'm gonna make a little star here and say this one, I'm just gonna put a star, and that star I'm putting problems for calculation. Problem for calc. Now, the reason why there's a problem is because whenever you deal with the calculations in chemistry, I gotta go for dinner, thanks, Mr. No problem, Weijie. You can always watch back later. So the problems for the calculation is like when you run the numbers, when you run numbers, always, it is always, when you run numbers, always spat out positive. Spat out positive. And that's really important, because what you have to do is you have to remember to flip. Remember to flip the sign. So they do this a lot at GCSE. They know it causes trouble, and it's just nice for me to make that point at this stage. Okay, so the third fact, now I've said that all reactions have a heat change. Fact number 3 is that there is a scale here, that the change can be big or small. And I know that seems odd because people go, of course it would be. But at this point, I'm emphasizing one in particular. And that's that because the change be big or small, the small ones are a problem. Because if you have a big enthalpy change, if you've got a massive minus 500 kilojoules per mole change there, and if I then have a minus 5 kilojoules per mole here, this one will probably not be measurable, probably not seen, because it's such a small value, and because heat is lost so readily in the environment that a small heat change becomes almost impossible to measure. And again, those questions appear regularly at GCSE. Okay, so at this point, I think it's good for me to go into some bond enthalpy calculations and to talk about bonds. So, okay, so my next part is bonds. So at this point, I pick up mexo-bendo. So mexo, I've got mexo, and notice that I'm actually changing I'm capitalizing and almost leaving a gap on purpose. So making bonds is exothermic. And that's really important. So when a bond is created, heat energy is released. Now, students often ask me why that is. And the reason being is that you're actually going from instability to stability. You have particles which are disconnected with high energies, often moving around rapidly. If I take two particles, A and B, and they slam together in a chemical reaction and they form a bond. If these two come together, they are becoming more stable. And when that comes together, it's the same like clapping hands. The particles had a huge amount of energy before, and when they slam together and join, I thought this started this. Hi, Donna. Sorry, I started it early. I apologize. Don't worry. So when these two particles slam together and form a bond, the energy is dissipated in that process. And the particles are going to both be slowing down, and they're going to be gaining stability and the energy. And if you're looking at this purely energetically on an energy scale, we're going to have particles with, if I just have this scale here as energy. Donna, I thought that when I sent out the link and when I started the video, it would, you guys would get the notifications, and you just kind of joined. You considering you've been off for the day, that was all. So if we look at particles A and B, and they have lots of energy, let's call this energy 10, and when they form together and make a bond, A bonding to B, what's going to happen is their energy is going to drop. They're going to have less energy because this is unstable. Shouldn't say unstable, should say unstable. High energy is unstable, and bonding, they're filling their outer shells. They're doing it because they benefited in terms of stability, and they're becoming more stable. And more stable means less energy. You always know this by if you take a year 7 student and feed them an entire bag of Haribo and you give them bucket loads of chemical energy in the form of sugar, you can just sit there and watch them as they bounce around the classroom. And they'll use that energy up in the process. And then once they've got through and they've lost all that energy, they will slow down again and they become more stable. So more energy, less stable, forming bonds, becoming more stable, less energy, therefore the energy drops. And let's say that if we pull this across here and read that as 3, I'm going to have released 7 kilojoules of energy, kilojoules per mole in terms of that reaction, and that would be exothermic. So making bonds is exothermic, and this is really, really important. We then follow the second rule. Of course, I always say mexobendo because it rolls off the tongue rather nicely. It's easy to remember. So breaking bonds. Breaking bonds is endothermic. And this makes, in terms of students, when I teach this, students often find that mexo is quite difficult to wrap their heads around. They struggle with the concepts of stability. They struggle with the concept of atoms and molecules forming bonds. They form bonds because they're going to be filling their outermost energy levels and therefore gaining stability, and then linking that stability back to energy, which will then explain why something is exothermic. And it's a rather long train now. It's a rather long thought process, and so students often struggle with it. But when I teach bendo, they often have absolutely no issue with this. If you have a bond between 2 atoms, 2 species, 2 molecules, if I have a bond and I want to separate them, I want to rip them apart and produce separate A and separate B. In order to break that bond, I am going to have to add energy. If you want to break anything, if you want to break a cup, if you want to break a brick, if you want to break a stick, if you want to break anything, you have to apply energy. It won't just do it on its own. And so students realize that a breaking process is endothermic. Now, that understanding is so fundamental to the understanding of energetics as a topic in chemistry. I really, really want to highlight its importance and significance, because if you can get a good understanding and if you can get a really good, solid knowledge, a solid knowledge of this, and it is really unshakable, it will be super useful in all of your studies from GCSE all the way through to your degree and PhD in chemistry. It's such a useful thing to have. And this now leads, of course, straight into my graphs. So we've got mexo and bendo, two different processes. Let's give them a couple of symbols. It's always nice to do so. So mexo, exothermic. So now all I'm doing here, folks, is reinforcing parts of the webinar. So I'm reinforcing that the minus delta H is exothermic in red, and a positive delta H is endothermic in blue. To remember, hot and cold, always nice. Okay, so this now leads us directly into our, I'll do that in black if I can. This leads us directly into our energetic graphs. Energetic graphs. So they're full of energy. Oh, sorry. So our energetic graphs, and there are two graphs for energetics. And not surprisingly, one for an exothermic reaction and one for an endothermic reaction. Now, what I'm going to do is I'm going to do each of them independently on the screen. So we're going to start off with exo. Let's start off with exothermic. Do you know what? I've changed my mind. I'm going to start with endothermic. Now, the reason being is it's an easier concept to understand. So if we go for endo first, this will make more sense and you'll see this. So endothermic graph, let's have a look at a very simple equation. Let's take, and you know what? Let's go for limestone. Let's go for thermal decomposition. So if I take calcium carbonate, test for the calcium ions is flame test, and it will give you a brick red flame test for the calcium 2+ ion. Test for the carbonate ion for CO3 2- is you add any acid and it will cause effervescence or fizzing, as I like to say. If I take calcium carbonate as a white solid, let's take 10 grams of this and we're going to heat it. Now, when you heat it, you're going to take that one substance, raise its temperature, all the particles will gain kinetic energy, they will vibrate more, and at a given point, those bonds will break. And I'm going to produce solid calcium oxide. This is white it's actually whiter than calcium carbonate. And I'm going to produce a gas of CO2. It's going to snap in half, and my mass will decrease. So if I produce 7 grams of calcium oxide, I will have produced 3 grams of carbon dioxide due to the conservation of mass law. We know that no mass can be created or destroyed, so it is simply just lost in different materials, or most of the time as gases. So we're going to do that. Let's have a look at what that looks like on a graph. So we're going to put calcium carbonate, on this axis is energy. Now, energy is measured in joules, the joule. And it's a capital J, of course, because it's named after a guy. I'm actually going to do it in kilojoules. The reason being is the joule is a very small unit, and kilojoules is far more useful. And, of course, our enthalpy change is measured in kilojoules per mole. So on the bottom is reaction. I could put reaction time, but they don't often do that. They do reaction point. So in this case, we can say reactants are over here, so, aka that is the start. So reactants are here, and we're going to have products at the end. We know that reactants go in and products are produced. And here's my limestone. So I'm going to heat up the limestone. I'm going to raise its temperature using my Bunsen burner flame. I'm going to add heat. And as that temperature climbs, temperature will increase until I reach a peak. Now, once I reach that peak, the top of that peak is important. So if in a chemical reaction, more bonds are made than broken, the reaction will be exothermic. Kim, that's such a lovely question. The answer is it's not entirely true. The reason being is you can't just count the bonds in terms of their number. You have to actually look at the values of the bonds themselves. If you broke 2 bonds of value 10 each, which would mean you've put in 20 kilojoules of energy, and you made 4 bonds of strength 2, that would still only add up to 8. So even though you made more bonds, it doesn't necessarily mean it's exothermic. We need to look at their values. But a great question. So I'm going to heat up the limestone. And most of the time, it's going to do absolutely nothing until I reach a critical temperature. Now, that temperature, this line here, is called, this arrow from this point here, from the energy, let's again keep it easy. Let's do 10 kilojoules. And I'm going to then read that as 22 kilojoules. This here is the activation energy. So I'm going to call this, I'm going to label this as A. That is the activation energy. So I'm going to, by the way, the symbol for activation energy is capital E for energy and little a for activation. I'll actually translate that as well. Activation energy. And this is the amount, the energy, activation energy is defined as the energy, the minimum, underline, minimum amount of energy, the minimum amount of energy required for a successful collision. Isn't that funny? I mean, collisions there, but I'm also then going to put required. I'm actually going to star that here, and so I'm going to star that in a different color because it's not particularly great there. I'm going to star that in a different color, and the alternative is the amount of energy required to break the original bonds, because all the bonds were there originally, and we have to break them. So the process is endothermic. Now, when we break all of those bonds, when we break them all, we then form a whole series of atoms. So every bond is smashed. All of them, the lot. I've got calcium on its own, carbon on its own, oxygen, oxygen, oxygen. All the atoms. I have dismantled everything. And now I'm going to put them back together. And I'm going to put them back together in a different order. And when I do that, I will then, new bonds are made, and I've now got my products. So in this case, calcium oxide and carbon dioxide. So now, in this case, I'm breaking them apart. This is quite clearly going to be endothermic. I've started off with one large product and formed two smaller, which means it will purely be down to the number of bonds that I had. But it's realizing that this arrow here, there is lots of these arrows require an awful lot of clarification, because notice that the upward one I've done in blue, I should have done this one in red, and this is B. That little red arrow there, so I'll need to actually label these on the notes. So A in this table is the energy activation. I'll put EA. It's always good to have that there. So this is activation energy / energy to break original bonds. Energy to break ORI bonds. It's always nice that. Should always be talking about bond entropy, really. So B is now the energy released when new bonds are made. Energy released when new bonds are made. New bonds are made. And then we went from 10 to 22. This is add 22. Add 12 kilojoules of energy. And then B has given us a lot less back. We've now gone from 22, and we've dropped now down to something like maybe 20, maybe 19. Not that I'll do 20. So this has released 2. So that has given out 2 kilojoules of energy. And you realize that the amount of energy that was needed to break the original bonds is less than the amount of energy that was released when the new bonds were made. So the process is endothermic. Now, the reason why this graph causes trouble is because we know in our minds with absolute crystal clarity that an endothermic reaction gets cold, but the graph is going up, and students don't like that. It adds in a source of misconception, a source of misunderstanding of how is it possible that something can get cold, and if it gets cold, why would the graph go up? Things going up are getting hotter. That's the train of thought students have. But remember, this is all about energy, and we know that endothermic reactions absorb it, which means it's starting low and ending high. Now, I'm going to come back to this on the exam questions. So there's our endo graph with all of our labels on it. Just one more label that we can use this graph, of course. And some people might say it's the most important, C. So what is C? C is the enthalpy change. That is the overall enthalpy change. That is the brackets overall energy change. So it's nice that the graph has got so much beautiful detail in it. Considering it's so simple and students just simply kind of just do this and they're like, I'm done with my revision. But there's a lot there to try and wrap your head around. Right, let's have a look at an exothermic graph. Now, you'll notice that I've just done a thermal decomposition there. I'm going to now do a displacement. No, let's do a, oh, it's a good one. Let's do a combustion. It's nice and easy. It's probably the most common one that you're going to see in your exams. So this is the exograph. So at this point, the exograph, because if you've got one, you've kind of got the other. This one's going to go down. We know that we're going to start off with the reactants. Let's have a look at what they look like. Let's put in methane. It's always a good point to start. And we're going to add oxygen to it. And that is, we're going to, first of all, we're going to take all of those compounds. Could you quickly go back to your endograph, please, so I can screenshot? Oh, Dana, of course you can. Of course I can. There you go. So I've put in methane as my fuel, and I put in oxygen. Now, guys, lovely rule. All, and I mean all combustion reactions. The word combustion means to burn. And if you burn anything, it's exothermic. So all of these graphs are exo. Every single one of them. So that is a whole lot easier. So if I just quickly go back to the exam specification points, which is a lovely addition to be able to expand on this, which is, notice that they have given down here and they have repeated it. Yeah, they have given 4 different reactions. Well, some of these we can just blanket, give them a symbol. So combustions are all exothermic. Notice I no longer need to write down the word exo or exothermic. I can just give it symbol. Would cracking be endothermic? Oh my, Sarah, oh my, what a lovely connection to make, Sarah. Cracking is endothermic. Taking a large single long chain hydrocarbon and breaking the bonds to form smaller pieces is endothermic. In fact, cracking is a type of thermal decomposition. Well done, love it. And so combustions are all exothermics. Thermal decompositions, I shouldn't do it in red. Do you know what? If you're going to color code things, keep it proper. Thermal decomps are all, shouldn't do thermal decompositions, such as cracking, brackets, cracking. This is turning out to be a cracking webinar. So we've got cracking. These are all endothermic. They require heat. Right. Okay, next one. Displacements. All displacements are exothermic. Students often ask me why that is. The reason being is a displacement reaction works on stability of compounds. Why would one thing swap with another? Now, you guys learn it in terms of reactivity. And if you link it to reactivity, that's perfect. The more reactive one is going to steal. And if it steals, then you're going to be forming a stronger bond. And the stronger bond you make, the more exothermic it will be. So all displacement reactions are exothermic. And we're going to now do the next two are now awkward. So dissolving salt, putting salt into water. The first thing I want to really mention here, folks, is number one, it can be endo or exo. It can be either. That's a problem. So you've got to watch out for the question. They will tell you if the temperature rises or falls. So endo or exo, and they're also very small changes. What that means, small change, difficult to measure. And that's really useful to know. Adding salt to water is a very difficult heat change to measure. Most thermometers will not be able to measure that temperature change. You'd have to use a digital thermometer. Most alcohol or mercury-based thermometers simply won't show that heat change, won't show that temperature change. Neutralizations are also either. So we can have endo or exo. So we can have either for neutralizations. I can add an extra rule there for those people who really like to learn those extra details, which makes your life in chemistry easier. You can almost predict exo or endothermic enthalpy changes for neutralizations depending on the products. If you make a gas like carbon dioxide, it will probably be endothermic. So, and that's for, by the way, that is an A-level rule, really, more than a GCSE rule, but it's lovely to have it. So, but displacements and combustions are always exothermic. Let's go back to my graph. Move over, get in there, there we go. So, what we now need to do is we need to, first of all, smash every bond. We need to destroy them all. And we're going to do this by adding energy. This is endothermic, hence why I do it in blue, because endothermics get cold. They absorb energy. I'm going to heat this up. Heat, 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 heat. Bang! I reach activation energy. And every bond now breaks. And I now form this picture. It's such a lovely picture to see. And I see this picture here. Now, what's interesting is you're about to see a whole load of balancing going on in the diagram. I apologize for that, but you'll see it as it happens. So we've had to add this energy. There's the endothermic activation energy. And now they're going to recombine. And they're going to form their new bonds. Now, making bonds, so when salt dissolves in water, they become chemically changed, as in bonds are made and broken. E. Kim, you are realizing some beautiful chemistry. So, just to explain what's happening, in dissolving, sorry folks, this is E. Kim's fault. You can blame her entirely for this. Dissolving. Here's what's happening, E. Kim. So I take, let's go for sodium chloride, Na+. I'm going to color code it. Na+, and then I'm going to change my color now to, I shouldn't do red and blue really, because it's not really Cl-, Cl-. So, E. Kim, the bonds I'm about to break are the electrostatic attraction between oppositely charged ions. Those bonds I now need, I'm not, oh no, sorry. Who is it? Kayun? No, who is it? Don't know. E. Kim, you have to help me. No, it's not E. Kim. Ka Kim, help me. Anyway, I need to break these. So I've now got to, when this drops into water, it's Kayun. Okay, Kim. Okay, sorry, Kayun. So I need to break those. So I need to rip those apart. This drops into water. And those bonds are ripped apart. Now, then you're going to say, so that process is endothermic. So ripping them apart is endo. So where does the exo happen? What is also happening, Kayan, is you're forming bonds to water. So let's now zoom in on one of these ions. So what the sodium is now forming is an electrostatic attraction to the water molecules, because water is actually polar, the oxygen is slightly negative. So it's going to form electrostatic attractions, the same type of bond that I had in the ionic compound in the first place, and it's going to make those with water, and it's going to make a lot of them. because water molecules are very small and they will surround that positive ion. On the chlorine side, so just to explain why the O's go for the Na like that, that's because the oxygens are slightly negative. The hydrogens in water are slightly positive. So what's happening in terms of the chlorine is this. The water molecules actually spin round and they form electrostatic attractions to the chloride ions like this. So we now have to, if you want to work out, this is A level now, Kayan, but it's lovely for that you've spotted it. You can calculate this using what's called a Born-Haber cycle or enthalpies of solution. You can work out the amount of the energy required to break, it's called the lattice dissociation enthalpy, the minimum energy required to separate 1 mole of an ionic solid into its gaseous ions. You can work out the amount of energy that is required for that. Then you can also calculate the energy released when it forms the electrostatic attraction to water. These are called hydration enthalpies, and calculate whether or not that solution is going to be exothermic or endothermic. So yes, they're not really chemically changing, by the way. It's in your GCSE exam. I need to, by the way, this is part of your GCSE, but not to this level. You guys simply have sodium chloride solid, which, by the way, my pen is too skinny. Sodium chloride solid being added to water goes to sodium chloride aqueous. That's all you guys learn at GCSE. Just to go the extra tiny mile, they can ask you for an ionic version of that equation, and an ionic equation version of it is going from solid to Na plus aqueous and Cl minus aqueous. So dissolving, by the way, please note it is on your specification. So it is deliberately there. There it is. It says specifically that you guys have to know that when you dissolve salts into water, that there is a heat energy change. And that's dead important. Okay, so at this point, moving over, going, there we go, going back to this. So we've smashed all the bonds in methane and oxygen. We've dismantled everybody. We put the line in blue because that bit's endothermic. I'm now going to make all the new bonds. And at this point, all the new bonds form. And we know that making bonds is exothermic. So, and the new bonds that I've formed, let's look at the compounds I have at the end. I'm going to form carbon dioxide, and I'm going to form water. Let's balance that equation. I have 1 carbon, I have 1 carbon, I have 1 carbon. That's okay. I have got 4 hydrogens, I have only 2 hydrogens. I'm going to make another water. Let's add another water to this. So another H2O. I'm going to put 2 in front of it there. Next, so all the H's now add up. Now check the oxygens. So oxygens, I've got 2 oxygens over here. And I have got 2 there, 4 in total. So I'm going to need to balance that as well with a 2 in front of the oxygen there. And it's nice to see my balanced equation of CH4 plus O2 going to carbon dioxide, the complete combustion of methane. And there's my complete combustion. And we've drawn all of it out in terms of its bonds. And we can clearly see it's going to be exothermic because the graph is going down. The energy released, of course, is this one. That the difference between those 2 lines is the heat energy that's going to be released. Notice that if we start at 22 and that drops now down to 12, I'm going to have minus 10 kilojoules of energy. So I'm losing energy because the number is dropping down. It's nice to actually see that in the graph, and hence the negative sign appearing. It's rather nice. Now we drop into actually, by the way, I need to balance this. I've suddenly realized if you're going to balance an equation, Mr. Duncan, if you're going to balance a diagram, do it properly, because I need more H, I need more O's. There you go. Need a few more O's up there, and I think that now all adds up, which is great. Cool. So, okay. Now we get to do burp calculations. So we now get to do bond enthalpy, bond heat energy calculations. And we pick up one really basic equation, and that is, of course, burp. So bonds, reactants minus products. Now, what this actually means is the B, I chose the B because this is bond data. Bond data. And bond data means that we need the actual equation, because the problem is I've got to be careful when I teach burp, because if I teach that, students write that down and they'll lose a mark. The actual equation is the enthalpy of reaction, B, equals the sum, this is the symbol for maths meaning sum of, the sum of the enthalpies of the reactants, the breaking bonds. Reactants, of course, you have to break up, break bonds. So sum of the delta HRs minus the sum of the delta H product. Sorry, not capital P, it's small p, low, it's subscript. And that's form bonds. So that actually is the real equation. Delta H reaction equals sum of delta HR minus sum of delta HP. But to make it easier to remember, I just remember it as burp. It's far, far, far more straightforward. Right. And at this point, I'm going to drop over to our preliminary work. Because in order for me to do this, I need data and I need a question. But it's nice the fact that I gave you a few of these in the booklet. So immediately I get you to focus on the data. So guys, that is bond data, and it has the word bond in it. Not very hard to, it's kind of hard to miss, to be fair. It also has pictures of bonds in it. So it's very easy to recognize. Then, of course, they have given us an equation with all the bonds drawn out. And all I really needed to do here was to count them. Now, notice that the first thing I did was I split the equation down the middle with a wiggly line. And I wrote reactants and products. Reactants and products. And I then said, right, let's start counting bonds. And you can see how I've counted them up. So I've counted them and then written them down here. So I have got 3, notice, 3, and I've color-coded this, folks, because, you know, I'm that awesome. So I've got 3 carbon-hydrogen bonds. I have got 1 carbon-oxygen bond and 1 oxygen-hydrogen bond. Those are all the bonds in methanol. And then, of course, I then had my oxygen bonds, being that I have 1.5 of the oxygen bonds. And I now multiplied them all up and added them all together. So I got a total for the energy required to break. This is the energy, this is the total energy needed to break ORI bonds, original bonds. Right, once I've worked out the amount of energy I'm going to have to input, the next thing is how much energy am I going to get out? Once again, I'm into counting bonds again. And I go, I've got carbon dioxide. I've got 2 carbon-oxygen double bonds, which are there. And I now have 4, and that's the tricky bit. I have got 4 here, folks, because I have a 2 in front of it. So I've got 2 water molecules. That could be drawn like this if you wanted. But of course, that Excel won't do that because it makes it too easy. That's 4 bonds there in total. 1 bond, 2 bonds, 3 bonds, and 4 bonds. They're not going to do that. They're just going to put a big number in front. So we've got 1 bond, 2 bond, but then you multiply them all up. So we get 4 in total. I shouldn't really erase that, should I? I don't see the point in erasing that, actually. There we go. So I can now count them and go, right, I've got 4 oxygen-hydrogen bonds. And I totaled them up. And then I just did burp to finish. Reactants minus products. Oh, which is not true. I've got it. I've written that in the equation literally backwards. So easy to do. Reactants 2132.5 minus 3338, and I get minus 1,206 kilojoules per mole. Now the 4 marks are for total of that, using and writing the equation, and the final value. So it's nice to see what they're doing. And these are purely theoretical calculations based on bond data. And hence why it fits into the column at this that I was talking about, the part of energetics as theoretical calculations. And that covers bond enthalpy calculations. For those students doing dual science, you don't need to worry about that. It's not on your spec, hence the bits in black. Okay, next bit. So now that we've done that, that brings us to the end of the theory bit. And we can now that we've done Burke, I can tick that off. We can now go into calorimetry. Okay, so the next part is practical heat energy measuring. And we call this calorimetry. So the word calorimetry is the name given to a practical. It's actually the name of the practical. It shouldn't really be put as a topic title, because it's not a title. It's actually the name of the actual practical you're doing. It's a bit like swimming. It is the name of the activity you're doing. And by the way, nice to actually just break it up into two words. The word calorie. You guys will recognize this, of course, from biology. And metry, meaning calorie, is, of course, you see that in foods, which is chemical energy, and metry meaning meter, to measure. So metry, to measure. So we've got calorie measuring, which is kind of cool. Okay, so there's two types of calorimetry. Calorimetry gets two of its own strands. Calorimetry. We have internal calorimetry, internal cal, and external cal. Now, you should have done both practically in lesson. If you haven't, ask your teacher to do some in the revision sessions, and they will happily do it. But they are they're similar in their nature, but two very different practicals. Let me explain. So the word internal calorimetry is the idea of where the heat source is. So internal calorimetry is the calorimetry where you are in a polystyrene cup and you have your thermometer in the middle, and you're often doing a reaction in fact, you're always doing a reaction in the calorimeter. And by the way, a calorimeter is the polystyrene cup. The cup is polystyrene. And of course, the reason for polystyrene, of course, is because it's a good insulator. It'll reduce heat loss. Good insulator. We wouldn't want to use a beaker, for example. Good insulator. So we've also, and the heat source, the reaction, the reason why it's called internal is because the heat from the reaction is being produced inside the actual measuring, inside the beaker itself, and it's not having to be caught by the water. The water is in with it. So it is called internal calorimetry, and it is far better than external because it has less heat loss. Don't know why that's just kind of done that. See if I can get rid of that again. There we go. And the top one's a thermometer, by the way. Thermometer. Okay, so now examples of this, of course, are key reactions you need to know, year 11. So we have magnesium and HCl, aqueous and metal. So that one there, of course, is a neutralization because the metal's acting as a base. We're going to form magnesium chloride and hydrogen gas. We're going to see fizzing, we're going to see a metal disappear. But this is a common one. So that one, of course, being exothermic, exo. The other one is copper sulfate, which is a blue solution, and zinc metal. Copper sulfate and zinc metal. This is another displacement, also a reduction, blimey, also a redox, loads of them. This is also exothermic, and all of these two reactions are done in the polystyrene cup. It is internal calorimetry. So what does external calorimetry look like? External calorimetry is done really for one reason. External cal is for combustion. We know that we can burn stuff. It's what I get paid to do. It's awesome. And when you burn stuff and you burn it, you will generate heat. Well, if I want to know, if I light a match, I have a match, and I want to know what is the enthalpy change? What is the enthalpy change for the lighting of a match? What I'm going to do is I'm going to strike the match and light it, and I'm going to collect the heat. I'm going to catch the heat in water. I'm going to catch the heat in the water. This is called external calorimetry. Now, the reason why it's called this is because the heat source, the reactions producing the heat outside of the water in which we are catching the heat in. What that means is there is going to be enormous heat loss. This one's going to be 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 heat loss. And these are going to be the few that get caught. So we always get huge discrepancies when you do external calorimetry for combustion reactions because the heat loss is so vast. There are other reasons as well. I said there were incomplete reactions, side reactions. Other ones include the heat capacity of water, which is quoted at 4.2. Of course, you're not just heating water, you're also heating the beaker, you're also heating the tripod and the gauze. So the heat capacity is an incorrect value because you're heating not just water. So loads of problems with this one. And again, you're going to measure the temperature at the start and at the end. Okay, this now drops us. So that's like a basic run through the two different kinds of practicals for measuring enthalpy change. The next thing is to run through the calculations. And this is poorly taught in general. The reason being is you guys get taught an equation. So this is calorimetry calculations, calorimetry calcs. And you guys learn one equation and you don't even learn it. The reason being is it's given to you. Q equals MC, shouldn't have capitalized it. Q equals MC delta T. So, and I need to just bring you now to realize that this Q is energy, raw energy in joules. M is the mass of water, which is where we're catching the energy. C is 4.2. That's the heat capacity of water, of H2O. And delta T, of course, is temp change. So, and this is all about water. Students often don't realize this, but what you realize here, folks, is all of those red arrows, all of the heat that is being released or being absorbed is either going into or being taken from the water. So we needed an equation that will calculate the energy change that the water is going through. So that will give us this equation here will give us the energy change, heat energy change in water. Notice my capitalization if people make mistakes, in the water. Right, the problem is that's not enthalpy. Enthalpy is the heat energy change under constant pressure, and it has a unit. Enthalpy is kilojoules, there's my energy, per mole. Now that unit gives us an equation, which is delta H, and here's the equation you've got to learn. Delta H equals Q over N. And those two equations, I cannot stress. Now, you don't have to learn that one. That one, you're given. You're given that. Don't learn it. But you are not given that one. And that one you need to make sure you remember. So at this point, I'm going to drop over to my, once again, to my preliminary work. So first of all, the diagram is clearly internal cal. It says internal calorimetry. Where's the water? Where's the water? I can't see the water. But internal cal. Next. So it then shows what things need to be kept the same. I'm tempted at this point to run through the preliminary work all the way through now, because it kind of brings me to the end and I can run some of the calculations. We have ticked everything off in that. We've given the definitions of exo-endo. We have discussed, we're currently discussing the calorimetry of combustion, displacement, dissolving, and neutralization. We're talking about the practicals. Using Q equals m so delta T, calculate the molar enthalpy change from the heat energy. Notice they don't give you the equation, the naughty, the mean. Then we've done drawing exothermic, the energy diagrams, energy level diagrams, the graphs. We've done mexo-bendo. We have talked about we've done burp, and we've mentioned these ones. So we've come to the end, so I may as well, at this point, I'm going to run through my preliminary work and link everything back to it. Okay, so the first question was an internal calorimetry. And it says, we're going to use this method above. The temperature, we're going to measure the temperature of 25 centimeters cubed of acid in the polystyrene cup, right? They put in some acid. Yeah, acid. So there's my acid. And we're going to measure out 25 of it. And they're going to add to that some sodium hydroxide. This is a neutralization. Neutralizations can be exo or endo. Most of them are exothermic, but any ones that produce gas will probably be endothermic. So it's nice to recall. And what's in this? It's going to add sodium hydroxide solution in 5 centimeter proportions until total of 30 has been added. State 2 properties of the sodium hydroxide solution that should be kept constant for each 5 centimeter portion. Okay, now the key thing here is the properties of the acid. Students would be likely to write down, you need to make sure that you add it at the same speed. And I'm like, that's not a property of the sodium hydroxide. If somebody said, what is a property of Dana? I'd say, she's a girl, she's got long hair. I wouldn't say how fast she runs. That's not a property of Dana. A property of a solution, temperature, melting point, boiling point, concentration, volume. All right, okay. Well, for each, we can't use volume. Students will put volume, lots of them will. But you can't because it says for each 5 centimeter portion. So volume's out the window. We can keep the concentration the same. And we can also keep its temperature the same. If I add boiling 5 centimeters of sodium hydroxide, that's going to give me a very different answer to if I put one in at room temperature. So those are the 2 properties I need to keep constant. Next. Right. Guys, please practice reading your thermometers and these questions are causing me right trouble. I'm just emphasizing a trick that Edexcel keep doing. Notice that this one here is the word before. This one's before and this one is after. So you'd expect them to go question 1 and question 2. Do they? No, they don't. They go after first. That's weird. This is after. How many people are going to put that value into there? Guys, you lose both marks if you get them backwards. That's mean. Watch out, please. Just be aware that they always tend to do that. So you read your thermometer. I'm not going to go over reading thermometers. It's up to you to practice doing it. Please do so. Right, next. The teacher said that only the results of experiment 3 showed the expected increase and decrease in temperature. There was no temperature decrease in number 1. Oh, that's interesting. Well, let's just consider what we've done here. We added 5, then another 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 5, and stop there. Well, I've started with 25 centimeters of acid, and I've added 5. A reaction will take place. Temperature rises. I add another 5, now down to 20, of course. I add another 5. A reaction will take place. The temperature will rise. And now we're down to 15. We add another 5. A reaction happens. The temperature continues to rise. Now we're down to 10. We add another 5. A reaction takes place. The temperature rises. We're down to 5. Last one, temperature rises for number 25. And then for 30, it's going to drop. No more reaction can happen. And this means that all we're going to end up happening is we're just going to be cooling this down now. No more reaction can occur. It's going to drop. That's the graph I would expect to see. Right. What happened here? Okay. It went up. 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 That's weird. So what could have caused that? The alkali was added too quickly. No, if I added the alkali too quickly, let's say we did it as 10, 10, and 10, even though we haven't, we've only got 5 at the end, what would happen? 10, 10, 5, and then a drop, drop, and drop. That would happen if we added the alkali too much, rather than the original. What would happen if the starting temperature was too high? If the starting temperature was too high, I would, the starting temp of the acid, be careful. The starting temperature of the acid was too high. Well, if we were measuring the temperature, it's really clever this. If you measure the temperature of the acid as 10 degrees, and then we add 5 to this, and we see it go up to 12, well, if I'd started at 12, if I did another one, and I had the thermometer originally reading 12, it would just go up to 14. It doesn't make any difference. So all the graph I would get is this. I would get exactly the same graph, just shifted up. The acid concentration was half what it should have been. Oh, that's clever. So if we had an acid which I had 25 centimeters cubed of the acid, and I thought it was 0.1 molar. Mole per dm cubed shouldn't do that for you guys. Moles / dm cubed. And I thought it was that. And I now add the acid to it. The problem is I'm going to add the 5, but if it was actually half as strong, I'm not going to need the full 25 to neutralize it. So I'm going to, by the time I've added the third one, all of it's used up, and it just plummets then all the way down, because I didn't have as many particles in the original acid. So it would have ended sooner. So what's the last one? The volume of acid used was 50 instead of 25. That makes sense, because if I've got 50 instead of 25, when I add the 5, I'm now down to 45. I add a further 5, and I'm now down to 40. I'm going to finish when I reach 30. There's 10, there is, I'm an idiot, 20 centimeters cubed of acid left, which means the reaction will never finish and therefore never drop. Really clever. This is right. The next thing. Why were the temperature increases in experiment 2 much greater than expected? Oh, I've just answered that with my previous graphs. The starting temperature of the acid was too high. Oh, hang on a sec, because it asked us the temperature increase in experiment 2. So what's experiment 2 done? Experiment 2 has gone, instead of going from 16, instead of going up by 1, 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 they're going up by 1 every time. Well, hang on, what's this gone up by? This one's gone up by 4.6. Whoa! Then it's jumped by 3.5, gone up by 3.5. Oh, guys, look, it's now dropping. Drop, drop, drop. Boom. Right. What did they do? Well, starting temperature of the acid, no, would have shifted it. The acid concentration was double. That's what it should have been. No, because if it was double that it should have been, then we would never have finished, and it never would have stopped. It never would have gone down at all. The volume of acid used was 50 instead of 25. Nope, would never have finished again. The alkali was added. We already saw it. If I added it in larger quantities, I'll see a big spike and then a big drop. That line here matches that line there. Neat that. That's hard though, folks. That's grade A stuff. People guess them. Next, lines of best fit. Plot your graphs. Not going to go over it. You guys need to learn how to plot graphs. Read the instructions. Do it properly. Right. Record the values. So it said plots on the graph. Yada yada. Record these values. The volume of it says exactly, and also the maximum temperature. Right. So volume of alkali added. I found where the point crossed over. I then read up on my graph from the line. Use a ruler, please, boys. And then read across. I can get the temperature and the volume. Just read them off. You're done. Next, right, we're into standard mole calculations now, folks. So we know there are 3 moles equations. Moles equals grams over grams. Moles equals C times V over 1,000. And moles equals V over 24. And in this case, it's a solution. So it's C times V over 1,000. We've got concentration. We've got volume. You've just got to work them through. So calculate the moles of acid. I have got 25, don't like the red, can't sign it into C times V over 1,000, and we spit out our moles. Nice and easy. Tick. Next. Right, it then asks for moles of sodium hydroxide. Well, that's why they've given us the equation, folks, because the equation says, so the acid is in a ratio of 1 to 2. I need twice as many moles of sodium hydroxide as I do sulfuric acid. I wrote down the ratio, did the times 2, so I times the moles of acid by 2 to get the moles of alkali. Done. Next, calculate the volume of sodium hydroxide needed. Well, I've just worked out its moles, and I've got its volume, I've got its concentration, which is up here in the previous question, which is there. There's the concentration of sodium hydroxide. Reorganize C times V over 1,000 to N times 1,000 over C gives me V. Spits it out in centimeters cubed, and we're done. External calorimetry making an appearance. There's the heat outside the beaker. So this one, write an incomplete combustion equation from methanol to carbon monoxide and water. It doesn't usually be, that's been really nice and giving you carbon monoxide, usually just has a toxic gas. So write the equation and don't forget to balance, and don't forget oxygen travels around in pairs. State another reason why the increase in temperature is less than expected. Heat loss to the surroundings. Well, hang on a minute. There are several reasons why. They gave an incomplete combustion. I like it. We're going to give the top answer of heat loss. If they asked for another one, we would say that the heat capacity is incorrect because you're heating the glass as well as the water. What else would I also say? There's no lid on it, so there's evaporation from the water as well. Lucas saying, sorry, he's late. Don't worry, Lucas, it's fine. You can always watch it back. Don't worry. So lots of good answers there, folks, but heat loss always the top answer for me, unless I'm pushed outside it. Right, and at this point, we come into calorimetry. And notice, we've got mass of burner before and after. Right, guys, I'm going to walk you through this here. So we have got Q equals MC delta T. And that is about water. Don't forget. Where's the water? Let's highlight that as yellow. Where's the water in the data? Mass of water. Temperature at the start. Temperature at the end. There's my water data. Let's input all of that here. Right. Q equals MC delta T. The mass of water was 125 grams. The heat capacity is 4.2. And my temperature change I am going to calculate, which I did here. 36 degrees. Run it into Q equals MC delta T, and it spits out in joules. Next, it then says, calculate the enthalpy change. There's a second equation. Delta H equals Q over N. Well, I've just worked out Q. That's nice. Can tie that in there. All I need now is moles. Well, where can I get moles from? This is moles of fuel. This is moles of reactant. Moles of reactant. Right. Where's my reactant? I'm burning methanol. Here's the mass. Let's highlight that. There's the fuel. Try that again. Here's the fuel data. Mass before, mass after. So I can work out how much fuel I burnt. So it started at 84.7 grams. It finished at 83.2 grams. So I burnt 1.5 grams. Right. It gave me the MR of methanol. Oh, that was nice of them. I can run this through grams over rams to give me moles. And then run it through delta H equals Q over N. But don't forget there's a trap. Because Q, we've just said, I'm going to put Q from here straight in up here. I can't do that. Because the units of enthalpy is kilojoules per mole. And I'm about to put in joules. So I need to divide by 1,000 first. And then input. So, and here's the trap. I mentioned this earlier. I do all that. And I get a value of 403 kilojoules per mole. And if I'm not careful, is there chemistry after school tomorrow? Of course there is, Lucas. So if I didn't remember, folks, I'd forget to put in the negative sign. This was exothermic. It was a combustion. I know it's going to be minus, but if you forget to put that sign in, you'll lose one of your marks. Next, right, it gave you a table. Now, I'm just going to warn you here, folks. They don't, at Excel, seem to do something really odd. They don't seem to like putting on the line. So just ignore the line for these. It says, identify two mistakes. Oxygen isn't on the reactant shelf, and it should be. And this is exothermic. That should be down here. So two clear mistakes. Next, we've already run that one, which is great. Another external calorimetry. There's the mass of water being shown. They're making you read a thermometer again, working out the temperature change. They've given you the volume of gas in centimeters cubed, folks. Oh, V over 24. Run it through to get your moles of gas. Delta H equals Q over N. You work out your kilojoules. You work out your moles. Don't forget to divide when you've got your Q equals MC delta T. Don't forget to divide by 1,000. There we go. Then it gives you a second one. Nice to talk about data books again. Student value is minus 510. The data book value is minus nearly 900. Big discrepancy. Natural gas contains other things that release energy when burned. Totally possible, but wouldn't really give a discrepancy that high because they're releasing energy as well. Not all the heat energy is transferred to the water. There's heat loss. Biggest one by a mile, guaranteed. Some of the water evaporates during the experiment. That is true. That will lower the temperature and the enthalpy change. But it's not going to cause a big enough discrepancy like that. The student measured the gas volume instead of the mass. You can use the volume, wouldn't make any difference. Next, another one, work out your bond net rates. Nice way to color code them. There's your 4 carbon hydrogen bonds. There's your 2 oxygen double bonds. Then you've got your carbon oxygen double bonds there. You've got your 4 oxygen hydrogen bonds, remembering to multiply it up. Yeah, and then burp to give you a value. Don't forget. Oh, this one you don't need to worry about the minus. It goes in for you, which is great. Burp does it for you. Notice the repetition, folks. Another internal cal. Q equals MC delta T. Just run it. Extract your data about water. You're good. It's given you, in this case, now it's given you grams of lithium oxide and an MR. So grams over rams. It's going to give you moles. There it is. And then you can work out Q over N. Don't forget to convert the joules into kilojoules. Watch out for that one. Oh, and this, yeah, there you go. There's the joules there. Don't forget to convert. And flip the sign, because I think the reaction was exothermic, was it not? The temperature change, temperature before was 16, temperature after it is exothermic. Don't forget to add your minus sign. Yeah, easily done. You can see the repetition. Finish the graph. Put the line at the other end. It's nice to do the whole thing. But all we want there is the products with the solution on it. Again, reading off the graph. This one was one of the hardest questions here. I'm going to go through this one. Right. So this question was kind of horrible. Student does an experiment to investigate how the temperature changes at different masses of solid potassium nitrate are dissolved in water. Okay. She looks at this graph to help her decide the mass of water and potassium nitrate to use in her experiment. Okay. The student decides to use a mass of 50 grams of water at a temperature of 25. Now, here's the tricky bit. Students are going to do one of two things. They're either going to go 50 grams of water, and they're going to match it up on the graph. And they're going to do that. And I'm going to do this let's do it in dark. Let's do it in blue. They're going to do that and read that off. Now, what I want to now focus on as to why this is an error, because it says use the graph to find the mass, not the temperature. If you chose 50, you'll read a temperature. That doesn't make sense. That should be the first. Oh, that's weird. How does that help me? It doesn't. I'm going to choose the temperature this time. Let's choose 25 degrees Celsius. Read up. That's going to spit out a mass of 37.5 when I read it off. Now, that's really clever. And everyone here now goes, I'm all over this. I'm going to write in 37.5. And they lose it. 50 grams of water, and the graph is 100 grams of water. It's a trap. Watch out. So we need to take the 37.5 and divide by 2. Done. Nice one. Hard that though. Tough. Next, plot the graph. Plot the graph. Draw the line of best fit. Read it off. Not difficult, folks. Change in 10 degrees. Can see how I've done it. I've done the line. Got started at 25. Went down to 10 degrees. It says from the graph, find the mass of potassium nitrate that would be needed to produce a temperature change of 10. So I go, right, the temperature change from 25 would be down to 15, and I can now read off the mass I want. Nice and easy. Explain how the student's results show that the type of heat change of reaction when dissolving water. The temperature is decreased, therefore it is endothermic. Draw the graph for it. It's going to go up because it's endo. Another Q equals MC delta T. Same thing, folks. Extract the data. Q equals MC delta T is about water. Mass of water. Starting temp of water. Final temp of water. Put them in. Yeah? And then you go, right, now I do delta H equals Q over N. Divide that by 1,000. Where's my moles? Mass of potassium nitrate. Do I have an MR? But I can at least work it out if I wanted to. Question doesn't even ask for it. Right. Wow, that was a long one. Let's drop back to and go share screen. Turn that off. Hey guys, thanks so much for hanging out with me, guys. I know it was a long one. That was about an hour and a half. That. Oh, Lucas, Lily is great. Thanks. I don't know where she is. I think she's actually getting a bath right now. But no, she's doing really well and settling in really well. But thanks for asking. I really appreciate that. Guys, thank you so much for hanging out with me today. I know it's been a long one, but I definitely think it was well worth going over. It's a tough topic, and I'd say it was definitely useful to watch back the webinar if you're stuck on any bits. Also, if you have any questions over the coming weeks, come and see me. I'll always give you the time of day. You know that, guys. During study leave, I'll always be in the labs. Come in and see me. I'll do some practicals with you one-to-one if it's helpful to help clarify some things. I can go over any questions that you need. Keep working hard. You're doing great. I know the exams are looming. Try not to get too stressed. Guys, have a nice rest of your evening. See you later, folks. Bye.